This is Physics 2, Lab 4, bar magnets. So the purpose of this lab is to measure the distance-dependent magnetic field of a relatively small bar magnet, and also to compare the observed versus predicted distances of the on and off axis magnetic fields using GlowScript and also our experimental measurements. So some of our initial results that we got was that n, or the slope, was equal to negative 2.76, k is equal to 1.023 times 10 to the negative 6, and then our magnetic dipole moment ended up being 5.1135 a times m squared, and the computed and experimental magnetic fields ended up varying greatly. So some of the equations that we used in this experiment are the Biot-Savart law, which describes the magnetic field generated by a constant electric current, and then we used the one for point charges. The magnetic field of a dipole, which is the model of an object that generates a magnetic field distinguished by two opposing poles, north and south. And then the magnetic field due to a bar magnet, which is distance dependent, as in the magnitude of the magnetic field decreases as the observation point is moved farther away from the bar magnet. So the setup for our experiment, we had measuring on-axis magnetic field, where we would place the bar magnet at one end of the meter stick, and then we used the Tesla meter app to measure the x-component of the magnetic field at various distances, and then we recorded the data for specific field strengths. And the second one was measuring off-axis magnetic fields. So we would adjust the setup to measure the field at a 45-degree angle from the original axis, and then record the measurements and correct the data to account for Earth's field. So here are some of our conditions for the experiment. Our assumptions are that Earth's magnetic field is the only other magnetic field needed to account for, that the phone was able to read and measure the magnetic fields properly, that the bar magnets act as a magnetic dipole, and that the magnetic field caused by a bar magnet falls off as the distance increases. Our system was the bar magnet, the phone that we were using the app on, and then we used a singular meter stick. And then our surroundings was everything else around the system, which includes the table, anything on the table, sometimes the floor. For our on-axis data, we measured when the x-component was at 20, 70, 120, 170, and 220, where we would record the distance and then the magnetic field at that area. And then for our graph, we ended up getting our slope equation, y is equal to negative 2.7627x minus 13.794. And then for our off-axis data, we ended up getting these at the 45-degree angle away, which we will then use in our GlowScript. So then we did our magnetic dipole moment calculations, where we used our slope from the on-axis data to find k as being 1.0227 times 10 to the negative 6, which we talked about earlier. And then we used that and we set the magnetic field equations for the bar and in general equal to each other to find that the magnetic dipole moment is 5.1135 a times m squared. So for our GlowScript code, we started with our magnetic constant, mu over 4 pi, 1 times 10 to the negative 7th, and then our magnetic dipole moment, we used this formula for it, and we put in our magnetic dipole moment of 5.1135 into it, and then we would create the magnetic field of a dipole on the bottom. We have our scaling here, where our magnetic field scale is equal to 1,000, and then our distance was 0.1, and then we had all of our observation locations of the positive x component distance, negative x component distance, positive y component distance, negative y component distance, and then both for the z. We then have our code that we use for our orange arrows and our purple arrows that we put the observation locations in for before. And then we would put in our pink arrow for our off-axis. And then that is what we got in our GlowScript shell. So from our results from GlowScript, we found that the off-axis field is 6.9 times 10 to the negative 2t, and then our measured off-axis field is 5.7 times 10 to the negative 5th t, so they are both vastly different. And some possible errors could have been other magnetic fields skewed the data, such as the field within the electric system at the table because it would charge things, and that the location of the magnetometer in the phone was inaccurate. Then our observations was that the magnetometer measures a near zero magnetic field in the x direction as it moves farther away from the magnet, and then vice versa, the magnetometer measures an increased x component of the magnetic field as it moves closer to the magnet. For our what ifs and why, what if you hadn't oriented your experiment to compensate for magnetic north and then had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? So our data would have been further skewed because Earth's magnetic field would have interfered with the bar's magnetic field. And what if we were able to stick two identical magnets together end to end and run the experiment again? Only the magnitude of the magnetic field would change and it would double, but the direction would stay the same.